In this section, we're going to be working on solving applied problems involving exponential growth and exponential decay. To help us out with this, right before this section in our notes, we have some formulas that are going to be useful for us to use. We have our exponential growth formula, our exponential decay formula, and Newton's law of heating and cooling. And then we have a doubling time formula for exponential growth and a decay rate and half-life formula. So we'll come back to all of these formulas as we move through the section, but one thing I did want to mention is to solve these exponential models, we're going to use the same four-step process that we did back in Chapter 2, Section 6, when we were solving proportionality problems. So remember when we went through those four things, and they were to select the appropriate model, find an ordered pair, and use it to solve for k. And then 3, we're going to save k into our calculator for later use. And then 4, we're going to use the equation from 1 and the k value from 2 to answer the question. We'll always be given half of an ordered pair and asked to find the other value. So it may be helpful for you to look back in your notes at a couple of examples back from Chapter 2, because we're going to be doing this exact same thing here, but with these different models. All right. So the first example we want to take a look at is a biologist started a bacterial culture with 100 bacteria. After 4 hours, there were 400 bacteria. If the growth rate is exponential, how many bacteria will there be in 48 hours? So we come back to our models here, and since we are getting more bacteria, we're going to be having exponential growth. So this is the model that we're going to select for example, or for our first example. So step 1 says we select our model, and since we have exponential growth, we're going to have this model, but then we also need to fill in what we know. So we know that it started with 100 bacteria. So that means our model for step 1 is going to look like P equals 100 e to the kt. So now step 2 is we need to find an ordered pair. So in this case, that's going to be a time and a population, so a T and a P that go together. And we know that after 4 hours that there were 400 bacteria. So our ordered pair is 400, and we're going to put that into our model and solve for k. So then this gives us 400 is equal to 100 e to the k times 4. So to solve this equation for k, we need to isolate our exponential by dividing both sides by 100, and that gives us 4 is equal to e to the 4k. So to undo an exponential base e, we have to use a natural logarithm. So the e and the natural logarithm reduce out, and we get the natural logarithm of 4 is equal to 4k. We divide by 4, divide by 4, and that gives us k is equal to the natural logarithm of 4 divided by 4. So I grab my calculator, and I go natural logarithm of 4, and then I divide that by 4, and I get this for my value. So I get that this is k is approximately equal to 0.35. Then step 3 says we put our k value back into our equation from step 1, so that's p equals 100 e to the 0.35 t. And then lastly, step 4 says we're going to answer the question. So our question said the following: we want P when t is equal to 48, because we want to know, well, how many bacteria, so what's the population going to be after 48 hours? So then that is p equals 100 e to the 0.35 times 48. So then I put that into my calculator, 100 e to the 0.35 times 48, and I press enter, and I get this number, and I'm like, yay! So I take this and I type it in, and then it tells me that I am wrong. Well, let's talk for a second about why that might be the case. So when we were looking at our four-step process, I actually didn't do this part right here. It said, save K into your graphing device to use for later. So what I did up here is I calculated my K, but then I rounded it to 2 decimal places. And you're like, well, how much error could that possibly have caused by not keeping the exact value? Well, let's go ahead and try this again. So if we go the natural logarithm of 4 and we divide that by 4, we get this number. To store that in our calculator, we notice right above the on key, there's another button labeled STO. Let's go ahead and press that, and notice it says answer and little arrow, and it's saying, okay, let's save this. Well, since it's the K, the proportionality constant, I'm going to hit alpha in my left parenthesis, and I'm going to save that in my calculator as K. So now notice, even if I press clear, if I go alpha left parenthesis to get K, my calculator thinks that those two things are exactly the same. So now, let's do this same thing, but let's use the K in the calculator. So P equals 100 e to the K times 48. And this time I have K in the calculator. So I type this in, and I have 100 e to the K, so alpha left parenthesis times 48, and I press enter. And when I do it this time, I get a very different number. So notice that the difference in the two numbers is about 300 million. So that's a lot of error. So the point of this is we need to be very, very careful with rounding. If we are not told explicitly to round, then we don't round. And we'll have to save these things into our calculator. If we are told to round, we need to round exactly as told. Otherwise, we're going to get rounding error, which is going to cause problems. All right. So let's move on to something a little bit different. We want to talk a little bit about doubling time. So for doubling time, let's start with our growth model, which is P is equal to P naught e to the k t. Well, if we want this to double, what we really want is we want t when p is equal to twice the starting amount, p naught. Well, that means we need to solve the following equation. Well, if p is equal to 2p naught, we're going to have 2p naught is equal to p naught e to the kt. And if we solve that equation, we divide by p naught, we divide by p naught, we end up with 2 equals e to the kt. And so we start solving this equation, but before we do, we notice something interesting happened out. For the doubling time, when we divided both sides by p naught, we noticed that this equation no longer depends on the starting amount or the starting population, P naught. So that's one of the interesting properties of exponential growth, is that the doubling time doesn't depend on the population. So we have the natural logarithm of 2 is equal to kt, and we divide by k, we divide by k, and this gives us that t is equal to the natural logarithm of 2 divided by k. So what this is telling us then is that the doubling time only depends on the growth rate. So the amount of time it takes to go from 1 bacteria to 2 bacteria, or from 2 bacteria to 4 bacteria, is going to be the same as the amount of time to go from 1 million bacteria to 2 million bacteria. So this formula, if we look, is right here on our formula sheet. So the doubling time for exponential growth is t equals the natural logarithm of 2 divided by k, which is exactly what we came up with here. So anytime we need to know the doubling time of exponential growth, that is going to be our go-to formula. So let's take a look at our next example. A fish population has a growth rate of 2% per year. How long will it take for the population to double? Well, our doubling time formula is t equals the natural logarithm of 2 divided by k, and our growth rate is 2% per year, so that means k is going to be, turning our percent into a decimal, is 0.02. So that gives us the natural logarithm of 2 divided by 0.02. When we grab our calculator, we have the natural logarithm of 2 divided by 0.02. We press enter, and we get the following value. So it's going to take a little more than 34.5 years. So let's go ahead and say about, and this is a pretty big approximation, 35 years. So make sure you are rounding to whatever value you are asked to do so. All right, let's take a look at our next example. So carbon-14 has a half-life of 5,730 years. A bone has 62% of its carbon-14 left. How old is the bone? All right, so let's go through our process. So this time, instead of exponential growth, we're going to be having exponential decay. Because we're not getting more carbon-14, we're getting less carbon-14 as it goes through its radioactive decay. So then we're going to select our model, P equals P naught e to the negative kt. So that's our step 1. So P equals P naught e to the negative kt. And notice it looks almost exactly the same as the exponential growth equation, except for our growth rate, k, is negative because it's getting smaller. So one thing that's worth noting, and it's common in radioactive decay problems, if we are given percents, not amounts, we assume P naught equals 100%, which is going to be, if we turn P naught into a decimal, is going to be 1. So that reduces our equation down to P equals e to the negative kt. All right, so then step 2 is we normally solve for k, and we can do that, but we have a nice formula that's going to help us out with our radioactive decay problems. So for our radioactive decay problems, we have that the half-life given by t and the decay rate k are related by k times t equals the natural logarithm of 2. So then that gives us that our decay rate is given by this. So if we need to find k, it's the natural logarithm of 2 divided by t, where t is the half-life. Well, what was the half-life of our carbon-14? 5,730. So this gives us the natural logarithm of 2 over 5,730. So we're going to go ahead and put that in our calculator. So natural logarithm of 2 over 5730. We press enter. And we get this number. And just to remind us, this e to the negative fourth means scientific notation. And that means times 10 to the negative fourth power. So this number would really be 0.000120968 on forever. So just be aware that that tells us we needed to move our decimal to the left 4 spaces, right? Okay. So regardless, we don't want to write it down at all. We're going to press our store key and save that in our calculator as alpha k. Step 3 is we just write down our equation. So we have P equals e to the negative kt, and k is in our calculator. So finally, step 4 is we need to answer the question. So the question is, how old is the bone when it has 62% of its carbon-14 left? So we want t when p is equal to 62%. But as always, we can't use percent, so then we change our percent into a decimal and we get 0.62. So then this gives us the equation 0.62 is equal to e to the negative kt, and we want to solve this equation for t. So we take the natural logarithm of both sides, and the e and the natural log reduce out. So we have the natural logarithm of 0.62 is equal to negative kt, and we divide by negative k, and we divide by negative k, so we get t is equal to the negative natural logarithm of 0.62 over k. So we put that into our calculator, so the negative, and we have the natural logarithm of 0.62 all over k, which we saved in our calculator. We press enter, and we get that the bone would be 3,951 years old. But let's go ahead and just round that to the nearest 10 years. So t is about 3950. So the bone is about 3,950 years old. All right, let's take a look at our next example. So example 4 is a cup of coffee with a temperature of 160 degrees is left in a room with temperature 70 degrees. After 10 minutes, the coffee is 150 degrees. How long will it take to cool to 100 degrees? So this time we're going to be using Newton's law of heating slash cooling, which is right here. So this one is very different from both exponential growth and exponential decay. So in this we have capital T and lowercase t. So we have to be a little bit careful. Capital T is the temperature. T naught is the temperature of the surroundings, so that's room temperature. T1 is the temperature of the object at time t equals 0. And K is the heating slash cooling rate, and T is time. All right. So in our equation, we're going to use this model, but we need to identify some of our things. So T naught is the temperature of the surroundings, or room temperature. So that's going to be 70 degrees. And T1 is the temperature of the object at the beginning. Well, that was the temperature of the coffee when this all started, which is 160 degrees. So for step 1, that gives us T is equal to T naught, which is the temperature of the surroundings, so 70 degrees, plus the initial temperature of the object, which is 160, take away the temperature of the surroundings, which is 70, times e to the negative kt. So we simplify that up a bit. 70, we simplify inside our parentheses. 160 take away 70 is 90 e to the negative kt. So that is our model that we're going to use. So now step 2 is we need to find a time and a temperature that go together. So we're told that after 10 minutes, the coffee is 150 degrees. So after 10 minutes, the coffee is 150 degrees. And we're going to put that into our equation to solve for K. So we have 150 is equal to 70 plus 90 e to the negative k times 10. So to resolve this equation, we need to isolate our exponential. So we minus 70, we minus 70, and we get 80 is equal to 90 e to the negative 10 k. We finish isolating by dividing both sides by 90. And we get 8/9 is equal to e to the negative 10k. We take the natural logarithm of both sides, and the e and the natural log reduce out. So the natural logarithm of 8/9 is equal to negative 10k. We divide by negative 10, divide by negative 10. So finally, k is negative natural logarithm of 8/9 divided by 10. I'm going to save that value into my calculator. So negative natural logarithm of 8/9 all over 10. And then I'm going to store that in my calculator as k. Alright, so now step 3 is I have t is equal to, and then our simplified equation was 70 plus 90 e to the negative kt, and k is in my calculator. So now, step 4 is I want to answer the question. So how long will it take to cool to 100 degrees? So for step 4, we want little t when capital T is equal to 100. So that gives us the equation 100 equals 70 plus 90 e to the negative k times t. And we need to solve for little t. So this is really similar to what we did in step 2. So we isolate our exponential by minusing 70 from both sides, and we get 30 is equal to 90 e to the negative kt. Divide by 90, divide by 90, and we get 1/3 is equal to e to the negative kt. We then take the natural logarithm of both sides, and the e and the natural log reduce out, and we have the natural logarithm of 1/3 is equal to negative kt. Dividing by negative k, dividing by negative k gives t is equal to the negative natural logarithm of 1/3 divided by k. So negative natural logarithm of 1/3 all divided by k, and we get the following number. So 93, so it will take about 93 minutes for the coffee to cool to 100 degrees. All right. So last example, example number 5, is doing an exponential regression. So this is going to work like all of the other regressions that we've done so far. The only difference is we are going to select exponential regression instead of linear, cubic, quadratic, or anything else. So after door-to-door canvassing, census workers determine the number of unoccupied homes. The table below lists the number of homes in millions that were unoccupied in 4 census years. So 1980, 1990, 2000, and 2010. So we're going to use 1980 as the year 0. So we have the corresponding input 0, 10, 20, and 30. And the number of unoccupied homes is 5.8, 7.3, 9.9, and 14.3. So this is going to be my L1s, and this is going to be my L2s. So we grab our calculator, and to put these in, we go to our stats menu, and we choose edit, and in the L1, we're going to have 0, 10, 20, and 30. And then in our L2, we have 5.8, 7.3, 9.9, and 14.3. So then after we have them put in, we go back to our home screen. So we go back into our stats menu, and instead of editing this time, we go over to calculate, and we're going to go down. So there's linear that we've done, quadratic, cubic, quartic, linear again, ln. So we're not asked to do it this time, but that's for a natural logarithm. Then we have an exponential regression and a power regression. So let's pick the EXP regression. We go L1, L2, enter. When we get down to store regression equation, we want to save this. So we go alpha trace, and we're going to save it as Y1, enter. Our calculator thinks for a second and gives us these values. So then to write down an approximation, it says that y equals a times b to the x. So our model, rounding to the nearest tenth, would be 5.6 times 1.03 raised to the x. And then B says use the function to project the number of unoccupied homes in the 2020 census. So for this year in 2020, that would correspond to 40. And we want to know the output. So we grab our calculator, we go alpha trace, we choose Y1, and we want to input 40. And if we input 40, we get the corresponding output of 18.68. And let's go ahead and round to the nearest tenth. So we would get 18.7 million unoccupied homes.